My sincere greeting to one and all. I am Tamanna from BSc Chemistry under second year. Today I am here with chapter Ultraviolet UV Absorption Spectroscopy. Introduction. One of the important field of activities of an organic chemist is the determination of structural formula of various substances. In the earlier days, the structure elucidation elucidation was mainly based upon the study of classical physical properties, melting point, boiling point, refractive index, etc., and the chemical reactions of the compound. The procedure involved was rather laborious and time consuming. However, in the last 50 years or some remarkable physical methods have been developed to serve as powerful tools for structure analysis. Of these, the most useful and commonly employed method are the spectroscopic methods, which are based upon the interactions of electromagnetic radiations with the substance under examination. These methods may further involve the study of electromagnetic radiations with the substance under examination. This method may further involve the study of ultraviolet UV, infrared IR, nuclear magnetic resonance, NMR, and mass spectrum. Mass spectroscopy is employed to determine the molecular mass and molecular formula. Mass spectroscopy is employed to determine the molecular mass and molecular formula of the substance, while UV and IR are used to determine the nature of functional groups. Finally, the NMR spectroscopy is used to know the complete structure, including the stereochemistry of a substance. The major advantages of employing this spectroscopic method for structure determination and identification of substance are as follows. First, they need very little time and the information obtained is often a permanent record in the form of a chart. Second, the substance is required in very small quantity of order 1 mg. Third, the method are extremely sensitive and highly reliable in establishing the structure of the compounds and analyzing of mixtures of closely related compounds. Fourth, they can be used for the detection and identification of even very short lived reaction intermediates. Fifth, during the spectroscopic studies, except mass spectroscopy, the compound is not generally affected chemically and can therefore be recovered unchanged. Sixth, continuous analysis of is often possible, calculating the study of a reaction rates, etc. In this chapter, we shall deal with the basic concept of ultraviolet spectroscopy, the electromagnetic spectrum and spectroscopic studies. First, electromagnetic radiations. Many spectroscopic techniques are based upon the interaction of a compound with light or some other form of electromagnetic radiations. It is well known that light and other electromagnetic radiations are different form of energy which have a dual character. They have the property of both a wave and a particle. They are called electromagnetic radiations because they consist of oscillating electric and magnetic field which are perpendicular to each other and perpendicular to the direction of motion of radiation. Some important characteristics of these radiations are: first, the energy of these radiations is inversely proportional to the wavelength or directly proportional to their frequency. Second, these radiations do not require any physical medium and can be transmitted through empty space. For example, light reaches us from the sun through empty space. Third, all type of electromagnetic radiations travel through space with the same velocity, which is nearly 3 into 10 to the power 8 meter per second. Electromagnetic radiation can be described in terms of their characteristics, such as a wavelength and frequency. First, wavelength. It is the distance between two adjacent crusts or trough in a particular wave. It is denoted by the symbol lambda. The wavelength is usually expressed in meters, micrometers, nanometer, or angstrom. 1 micrometer is equal to 10 raised to power minus 6 meter. 1 nanometer is equal to 1 into 10 raised to power minus 9 meter, and 1 angstrom is equal to 1 into 10 raised to power minus 10 meter. An older term for micrometer is micron. 1 micrometer is equal to 1 micron. And an older term for nanometer is millimicron. 1 millimicron is equal to 1 nanometer. Second frequency, it is the number of waves which pass across a point in 1 second. It is denoted by symbol V. Normally, the frequency is generally expressed in cycles per second (CPS) or simply second inverse or hertz. 1 hertz is equal to 1 CP. The frequency and wavelength are related to each other such V is equal to C upon lambda, where C is the constant velocity of light. Third, wave number. It is the reciprocal of wavelength and represents the number of waves per centimeter. It is denoted by the symbol B bar. Wave number is generally expressed in terms centimeter inverse reciprocal centimeters. Wave number is related to wavelength and frequency as V bar is equal to 1 upon lambda is equal to V upon C, where C is the velocity of radiations in centimeter is 3 into 10 raised to power 10 centimeter per second. In SI system, the unit of wave number is meter inverse. Fourth, energy of electromagnetic radiation. Electromagnetic radiation are associated with the discrete energy unit called quanta or photon. The energy of a photon is directly proportional to its frequency or inversely proportional to its wavelength, as shown by the following equation. E is equal to hv is equal to hc upon lambda, where h is the Planck constant whose value is 6.625 into 10 raised to power minus 34 joule per second. Electromagnetic spectrum. Visible light which can be detected by human eye constitutes of a very small part of electromagnetic radiation. The full range of these radiation is indeed very large and their wavelength vary from a very small fraction of a meter to many kilometers. The arrangement of entire range of electromagnetic radiation in increasing order of the wavelength or decreasing order of their frequency is known as electromagnetic spectrum. The complete electromagnetic spectrum, along with common names used to identify different range of wavelength, is shown below. Approximate range of wavelength and frequency of electromagnetic radiations note to scale. Of the complete electromagnetic spectrum, spectroscopy techniques are concerned primarily with radio frequency radiations (NMR), infrared radiations (IR), and ultraviolet visible radiations (UV). Principle of absorption spectroscopy. It is interesting to note that practically all the important spectroscopic methods are used for structural analysis belong to the field of absorption spectroscopy, which studies the absorption of electromagnetic in relationship to molecular structure. When a beam of electromagnetic radiation is passed through a substance, the radiation may be either absorbed or transmitted depending upon the wavelength of the radiation and molecular structure of the substance. Absorption of radiation would naturally bring about an energy increase in the energy of the molecule, the energy gained being directly proportional to the frequency or inversely proportional to the wavelength of radiations. The increase in the energy of the molecule may lead to the electronic excitation, whereby electrons are raised to higher energy levels. Alternatively, it may bring about an increase only in the vibrational or rotational energy of the molecule. Electronic exhibition can be caused by only high energy radiation such as ultraviolet and visible radiation. On the other hand, vibrational and rotational energy levels can be raised even by relatively low energy infrared radiations. A very important condition for a molecule to absorb electromagnetic radiation is that the energy of a photon of the radiation must be equal to the energy difference between two vibrational or rotational or electronic energy state of the molecule. In other words, the particular wavelength of a radiation that a electronic energy state of the molecule. In other words, the particular wavelength of the radiation that a given molecule can absorb is determined by changes in vibrational or rotational or electronic states that are permitted to a molecule of that structure. The absorption of radiation is observed instrumentally by passage of radiations through a sample of substance and automated analysis of this intensity of transmitted radiation. A record of this amount of radiation observed or transmitted by a given sample as a function of wavelength of radiation is called absorption spectrum. One might accept an absorption spectrum to consist of a series of lines, but actually the spectrum is made of absorption band with peaks of maximum intensity. The instrument used for recording a spectrum is known as spectrophotometer or spectrometer. Having discussed the principle of spectroscopy, we proceed to discuss about ultraviolet spectroscopy in some detail. Ultraviolet spectroscopy involves the measurement of absorption of light in the visible and ultraviolet region. Visible region 400 to 800 nanometer, ultraviolet region 200 to 400 nanometer by a substance under investigation. Since the absorption of light involves the transition from one electronic energy level to another within a molecule, UV spectroscopy is also known as electronic spectroscopy. It will be quite appropriate at this stage to study the law which governs the absorption of light. The absorption law. These are the two laws which express respectively the relationship between absorption of light by a substance and its molecular concentration and the length of the path through which the light passes. They are first Beer's law. According to this law, when a beam of monochromatic light is passed through a substance dispersed in a non-absorbing solvent, the absorption of light is directly proportional to the molecular concentration of the observing substance. Second, Lambert's law. This law states that when a beam of monochromatic light is passed through a substance, the absorption of light is directly proportional to the path length of the sample of the substance. Third, Beer's-Lambert's law. The two laws stated above can be combined to give a general absorption law termed as Beer-Lambert's law. It may be stated as the absorption of light by a substance at a particular wavelength is proportional to the number of molecules of the substance in the path of light. Mathematically, log I naught upon I is directly proportional to C. Beer's law. Log I naught upon I is directly proportional to L. Lambert's law. Beer-Lambert's law may be expressed as log I naught upon I is directly proportional to C into L. Log I naught upon I is equal to epsilon C into L. This is read as epsilon, or where I naught is the intensity of incident light, I is the intensity of transmitted light, C is the concentration of observing substance in mole per liter. Inversion, L is the path length or thickness in centimeter of the cell containing the sample. Epsilon is the proportionality constant as molar absorption, sometimes referred to as molar extension coefficient or simply extension coefficient. The term log I naught upon I is termed optical density or absorption A. It is the measure of absorption of a radiation by a sample. Therefore, Beer-Lambert's law may also be expressed mathematically as A is equal to log A I naught upon I epsilon E L. Limitations of Beer-Lambert's law. Beer-Lambert's law is strictly obeyed when dealing with the UV spectra of single species. However, if a sample containing different structural form of the molecules in equilibrium with each other, such as in case of ketoenol tautomers, the law is not obeyed. It is not applicable if the solute sample and solvent intersect with each other to form complex. Molecular absorptivity. It is the proportionality constant which related to the observed absorption A at the particular wavelength lambda to the molar concentration of the absorbing substance and the length L of the path of light in centimeter. It may be expressed as epsilon is equal to log I naught upon I whole divided by CL is equal to A upon CL, where log I naught upon I is also equal to A. Molar absorptivity is a measure of the intensity of absorption at a particular wavelength and has the dimensions of centimeter square mole inverse, but these units are seldom used. It is a characteristic property of a compound and is not affected by its concentration or the length of the path of light. Its value ranges from 0 to 10 raised to power 6 values. About 10 raised to power 4 constitute high intensity absorptions, while values below 10 raised to power 4 are low intensity absorptions. Percent transmission, since I naught upon I is the ratio of intensity of incident light I naught to the transmitted light I, the transmission T of the sample will be naturally given by the relation T is equal to I upon I naught. Percentage transmittance is equal to 10 into I upon I naught. Here is a problem. The molecular absorption of a conjugated diene's molecular mass is equal to 10 into 110 gram per mole is 1300 13,100. Compute the concentration of these dienes in methanol, which is required to give the absorption of 1.6 path length of the light is 1 centimeter. Express your answer in mole. First in mole liter inverse and second is gram liter inverse. According to Beer's law, A is equal to epsilon C into L. We will substitute the values. The answer will be 1.22 into 10 raised to power minus 4 mole per liter, and the second one will be 1.23 into 10 raised to power minus 5 gram per meter length inverse. Mechanics of recording the UV spectrum. Presentation of the spectrum. Excellent ultraviolet spectrometers are now available, which can be conveniently record the spectrum over the range of 200 to 800 nanometer or 240 nanometer is known as near ultraviolet region, and 400 to 18 nanometer is visible region. Since oxygen of the atmosphere strongly absorbs light at about 200 nanometer, below the use of wavelength shorter than 200 nanometer for ultraviolet region, it is not practicable unless special vacuum techniques are employed. The ultraviolet spectra are always recorded on the wavelength scale in millimeter or nanometers. Procedure for recording the ultraviolet spectrum. The given compound is generally dissolved in some suitable solvent which does not itself absorb light in the region under examination. The commonly employed solvent are 95% ethanol, hexane and water. The solution of the compound is placed in a suitable transparent container which does not absorb light in the region being studied. Generally, a quartz cell of 1 cm path length is used for this purpose. Glass cannot be used since it absorbs strongly in ultraviolet region. At the same time, some solvent is taken separately in other quartz cell which serve as a reference cell. Sometime sample solution and the solvent are then exposed to the ultraviolet and visible radiation in a spectrophotometer, in which a hydrogen discharge lamp is usually employed as a source of light in the ultraviolet region 200 to 400 nanometer, while a tungsten filament lamp is used for the visible region 400 nanometer to 800 nanometer and of the radiation. The spectrometer operates a comparing the amount of light in a beam transmitted through the sample with the reference beam which passes through the reference cell. The compensates for any absorption of light by the cell and the solvent. In this way, the spectrometer measures the amount of light absorbed by the compound at each wavelength of ultraviolet and visible region. This absorption gets recorded on the chart part as a plot of wavelength of the entire region on the horizontal axis versus the absorption A of the light at each wavelength on the vertical axis. spectrum obtained consists of a small number of broad peaks. Quite often only one peak is seen. UV spectrometer. A simplified diagram of UV visible spectrometer is shown in figure 4.2. It consists of the following parts. First, a source of radiation which emits all wavelength of UV or visible radiations. The commonly used source of light in the UV region is hydrogen or deuterium discharge lamp, while a tungsten filament lamp is used for producing visible light. Second, a monochromator which separates the radiation into individual wavelengths. The single wavelength of radiation is split into two beams, one of which passes through the sample cell while the other passes through the reference cell. Third, a detector which continuously measures the intensity of the ratio of beam transmitted through the sample and the solvent respectively. Fourth, a recorder chart paper which automatically records the absorption of light at each wavelength as a graph of absorption varies wavelength. UV spectrum is source of radiation, monochromator, reference cell and sample cell, detector or recorder. Presentation of the spectrum. The ultraviolet spectra of 1,3-butadiene in hexane shown in figure 4.3, it may be seen that absorption of ultraviolet radiation by 1,2,1,3-butadiene being at wavelength below 200 nanometer and continuous up to the 260 nanometer. The absorption is maximum at 230 nanometer top at the peak value as shown in the diagram. The ultraviolet absorption spectrum of 1,2,1,3-butadiene is shown. The maximum lambda max is obtained at 217 nanometer. The spectrum is reported as a single absorption peak using the notation lambda max is equal to 217 nanometer. In the reporting of ultraviolet UV spectrum for analytical purpose, the molecular absorptivity epsilon, which indicates the intensity of the absorption of the wavelength of maximum absorption, is also quoted along with lambda max. For example, the molar absorptivity of 1,3-butadiene at lambda max is equal to 217 is 20,900. Therefore, the UV spectrum is reported as 1,3-butadiene lambda max is equal to 217 nanometer or epsilon is equal to 2,900. Sometimes the ultraviolet absorption curve are also present by plotting the molecular absorbivity against wavelength. For example, the ultraviolet spectrum of acetone in hexane plotted as epsilon versus wavelength is shown below in figure 4.3a. It may be seen that the maximum molar absorptivity epsilon is about 15 at lambda max is equal to 279 nanometer. The ultraviolet spectrum of acetone in hexane, epsilon versus lambda. Since the UV spectra generally show broad peak and valleys, the actual spectra are rarely used. The spectral information is given by listing the value or values of lambda max along with the molecular absorptivity for each value of lambda max. Principle of UV spectroscopy. Absorption of visible and ultraviolet light produces change in the electronic state of molecules associated with the excitation of an electron from a lower to a higher energy level. But it must be noted that each electronic level in a molecule is associated with a number of vibrational sublevels with small energy separation, and each vibrational level in turn is associated with a number of rotational sublevels with still smaller energy separation. Therefore, in its transition to higher energy level, an electron can go from any two of the subcell corresponding to various vibrational and rotational states in the ground state to any of the sublevel in the excitation state. Appearance of broadband and not sharp peak in the spectrum. In the electronic excitation in the molecule had occurred without any accompanying changing in vibrational and rotational sublevels. The spectrum would have rotational sublevels. The spectrum would have consist of sharp lines, as in case of absorption spectra of atom, with each line representing a change in electronic state, but due to the mixing of vibrational and rotational changes with electronic change in the molecule. Therefore, there will be a large number of possible transition requiring only slightly different energies. This will require the absorption of a large number of wavelengths which are very close to each other. As a result, the absorption spectrum consists of large number of lines which are too close together to distinguish spectrally and are recorded in a form of broad bands in the spectrum obtained. As stated earlier, the spectrum is described in terms of position of the top of hump lambda max and the molar absorption epsilon max. Electronic exhibition. Electronic transition involves the promotion of an electron from one orbital to another orbital of higher energy level in a molecule. Of electron promoted may be a alpha pi sigma electron, an electron from in a present in a sigma molecular orbital, and a pi electron, an electron present in a pi molecular orbital. Or third, an electron present in non-bonding orbital, as illustrated with the help of electron pair in formaldehyde as shown the right hand side. The higher energy orbital are anti-bonding molecular orbital, which may be vacant in the ground state of the molecule. The anti-bonding orbital associated with the pi sigma bond is called sigma star orbitals, and that associated with pi bond is called pi star orbital. Since the n electrons are not concerned in bond formation and there are no anti-bonding orbital associated with them, the electronic transition takes place in the ultraviolet and visible region are in the following type: first, sigma to sigma star; second, n to sigma star; third, n to pi star; and fourth is pi to pi star. 4.5 gives a general idea of relative amount of energies required for various type of electronic excitations. A brief account of the various type of electronic transition is as follows. First is sigma to sigma star transition in which a sigma bond electron is excited to an anti-bonding sigma star orbital are called sigma to sigma star transition. This transition can be shown only by the compounds such as saturated hydrocarbons, in which all valence shell electrons are involved in the formation of sigma bond. The energy required for this transition is very high, and consequently these occur at a very short wavelength. For example, in methane, the absorption of energy or for such transition occur at only 125 nanometer. Example is shown below. Since these wavelengths are lesser than 200 nanometer and fall in the vacuum UV region, the usual spectroscopic technique cannot be used in case such transition. Second, n to sigma star transition. These are the electronic exhibition from a non-bonding atomic orbital to an anti-bonding sigma star orbital compound having no bonding electron on heteroatoms such as oxygen, nitrogen, sulfur, or halogens can shown n to sigma star transition. These transitions are of lower energy and hence occur at longer wavelength than sigma to sigma star transition. For example, n to sigma star transition in methyl chloride requires absorption energy at 174 nanometer. The energy required for this transition decreases with the decrease in electronegativity of the heteroatom, and therefore the wavelength of absorption increases. For example, methyl chloride absorbs at 774 nanometer, while in methyl iodide absorption takes place at 258 nanometer. Similarly, amines absorb at higher wavelength than alcohol, and nitrogen has lesser electronegativity than oxygen. The observation can be attributed to the fact that greater the electronegativity of the heteroatom, more firmly the non-bonding electrons are held by it, and therefore more energy is required to n to sigma star transition. Hydrogen bonding of the compound with the solvent also shift the absorption of shorter wavelength, but in general n to sigma star transition are not much important. Third, n to sigma n to pi star transition. These are the transition in which the electron in the non-bonding atom orbital is promoted to an anti-bonding pi star orbital compound having double bond between heteroatoms. For example, C double bond O, C double bond S, and C and double bond O shows this transition which appear as weak absorption bands. These transitions require only small amount of energy and take place within the range of ordinary ultraviolet spectrophotometer. However, the intensity of absorption is generally very low. For example, the carbonyl group of saturated aldehyde or ketone exhibits an absorption of low intensity at about 285 nanometer. Fourth, pi to pi star transition. The transition in which pi electron is exhibited to an anti-bonding pi star orbital are called pi to pi star transition. These have relatively higher energy requirement than n to pi star transition, and absorption generally take place outside the ordinary ultraviolet region for simple molecule containing isolated unsaturated centers, but the intensity of absorption is very high. For example, the pi to pi star transition for simple aldehyde and ketone produces an absorption band of high intensity and about 180 nanometer. For a simple alkene like ethylene, such a transition takes place in still for far ultraviolet region about 175 nanometer. Effect of conjugation. Conjugation of double bond lower the energy required for the electronic transition. As a result, molecules containing conjugated systems such as C double bond C, single bond C, double bond C R, and C double bond C, single bond C, double bond O observes the radiation of longer wavelength than in case of non-conjugated systems, and absorption band appear in an ordinary ultraviolet range. For instance, 1,3-butadiene shows lambda max 217 nanometer in contrast to O ethylene, which showed lambda max 175 nanometer. To understand the effect of conjugation on lambda max, let us start the ethylene, which is the simplest unconjugated alkene. The double bond in ethylene consists of sigma bond formed by the combination of sp2 hybrid orbital of two carbon atom and a pi bond formed by the combination of unhybridized 2p orbital. Due to the large difference in the energies of pi bonding and pi antibonding molecular orbitals, figure 4.6, pi to pi star transition take place with the absorption of radiation below 200 nanometer, 175 nanometer for ethylene. Therefore, these exist only far ultraviolet region. In a conjugated system such as 1,3-butadiene, there are two ethylene under units in conjugation with each other. Due to the conjugation, the pi bonding orbital of these two ethylene units intersect with each other to form two new bonding orbital. Pi 1 and pi 2 are different energy. Similarly, these formation of pi star orbital, pi anti-bonding orbital, pi star second, pi star 3 and pi star 4, two of different energy form the two ethylene unit. The energy difference between highest occupied pi molecular orbital HOMO and the lower occupied molecular orbital LOMO for 1,3-butadiene is less than it is for ethylene. As the HOMO and LOMO energy gap becomes smaller, the position of energy absorption moves to longer wavelength, 217 nanometer for 1,3-butadiene, which falls within the ordinary radiation region. Higher energy P to pi star transition, shorter wavelength. Lower energy pi to pi star transition, longer wavelength. Comparison of pi to pi star transition energy in ethylene and 1,2-butadiene. With the increase in the number of double bond in the conjugation, the energy difference between HOMO and LOMO further decreases, so that absorption moves to still longer wavelength. Thus, spectrum of 1,357 octatetraene in hexane exhibit lambda max 290 nanometer, epsilon max is equal to 552,000. If there are enough double bond in conjugation, absorption will ultimately move into the visible region and the compound will be colored. For example, beta carotene, a naturally occurred yellow pigment containing 11 double bonds in conjugation owes its color to absorption in a visible part of light, lambda max 455 nanometer. Another effect of conjugation is that the increase in conjugation, the number of UV transitions increase and the spectrum become more complex. To sum up the above discussion on electronic transition, it may be stated that organic chemist is primarily interested in two type of transition, particularly in conjugated system. These are N to pi star, for example, C double bond O to C double bond O, and pi star to pi star, for example, C single bond O. It may be noted that transition at anti-bonding pi star orbital are associated only with unsaturated centers in the molecules. Transition probability. It is interesting to note that it is not necessary that exposure of a compound of ultraviolet or visible light may must all lead to the exhibition state. In other words, on the other hand, the probability of a particular electron transition depend upon the value of molar absorption epsilon max and certain other factors. According to the transition has been divided into categories. First is allowed transition and second is forbidden transition. First, allowed transition. These are the transition which have epsilon max is 10 raised to power 4 or more. The probability of these occurrence is very high. They are generally due to the pi to pi star transition. For example, pi to pi star transition in 1,3-butadiene, which shows absorption at 270 nanometer and has lambda max 20,900, represents an allowed transition, and the pi to pi star orbital involved in these transitions lie in the same plane and can undergo overlapping to a large extent in the excited state. Therefore, pi to pi star transition are highly probable. Second, forbidden transition. There are transitions for which epsilon max is generally less than 10 raised to power 4. These are usually related to N to pi star transition. For example, N to pi star transition are saturated aldehyde or ketones showing weak absorption near 290 nanometer and having epsilon max less than 100 is forbidden transition. It should be clearly understood for that forbidden transition does not mean that such a transition cannot take place at all. It just tells us that the probability of transition is very low. To clarify the statement, let us consider the N to pi star transition. The orbital containing the non-bonding electron present on the heteroatom lie in the plane perpendicular to the plane of pi star molecular orbital. The region in the space belonging to these orbitals can overlap only to a very small extent. As a result, the probability of extension of an electron to pi star orbital is very low. Concept of chromophores and exochromes. First, chromophores. The term chromophores was originally used to denote the functional group or some other structural features, the presence of these of which imparts a color to the compound. For example, nitrogen group is a chromophore since it present in the compound imparts yellow color to the compound. But these days the term chromophore is used in much broader sense. It is now defined as any group which exhibit absorption of electromagnetic radiation in visible region or ultraviolet region. It may or may not impart any color to the compound. Table 4.1 listed some sample chromophores gives along with their lambda max, epsilon max and the type of transition involved. This is the table. First, chromophores, their transitions, approximate value of lambda max in nanometer, approximate value of epsilon max, and the solvent. It may be seen that chromosomes are of two types. First, chromophores such as C double bond C and C triple bond C, which consist pi electron and undergo pi to pi star transition. Second, chromosomes such as C double bond O, N double bond O, and NO2, which contain both pi and n electron that can undergo pi to pi star as well as n to n star, n to pi star transition. Two compounds having the same chromosomic group generally exhibit absorption at nearly the same wavelength lambda max, but have nearly the same molecular absorption epsilon max. Therefore, it should be possible to identify the presence of a particular function such in a group in a unknown compound by the compound of UV spectrum, which with the data of already known compound, but the position of absorption maximum and the intensity of absorption of the modified by the number of factors as discussed below in section 1.9.3. Oxochromes. An oxochrome is a group which itself does not act as a chromosome, but when attached to a chromosome, it shifts the absorption maximum towards longer wavelength, along with an increase in the intensity of absorption. Some commonly known exochromic groups are OH, NH2, OR, NHR, and NR2. All oxochrome contain only one or more non-bonding pair of electrons. When an oxochrome is attached to a chromosome, it leads to the conjugation or help in extending conjugation by sharing of its non-bonding pair of electrons as shown below. Due to the conjugation, there is a decrease in energy difference between the ground state and exhibited state of the group. As a result, the absorption shifts to the longer wavelength. At the same time, there is a increase in the intensity of absorption. For example, when oxochrome NH2 group is attached to the benzene ring, it increases lambda max as well as epsilon max as shown given below. Benzene aniline lambda max is equal to 255 nanometer increases to lambda max 280 nanometer. Epsilon max is equal to 203 nanometer increases to epsilon max is equal to 1430 nanometer. NH2 act as a oxochrome by extending the conjugation in benzene by the participation of non-bonding pair of electron in conjugation. Similarly, ethoxy group OC2H5 act as an oxochrome as shown given below. Azobenzene, para-ethoxy, ethoxy-azobenzene. Lambda max 320 nanometer increases to lambda max is equal to 385 nanometer. Epsilon max is equal to 21,000 increases to lambda epsilon max 42,000. Change in position and intensity of absorption. For isolating chromophone in groups such as C double bond C and C triple bond C, absorption occur in fair ultraviolet region which can not be easily studied, but the position of the absorption maximum and the intensity of absorption can be modified in different type of some structural changes or change of solvent. These changes can produce four kind of effect. First is bathochromic effect or red shift. Second is hypochromic effect or blue shift. Third is hyperchromic effect, and fourth is hypochromic effect. These effects are discussed below. First, bathochromic shift or red shift. It involves the shift of absorption maximum toward longer wavelength. It can be brought about the three different methods as given below. First, by attachment of a oxochrome to the chromosome. When an oxochrome such as OH or NH2 is attached to a chromosome, it leads to the conjugation or help in extending the conjugation. As a result, absorption spectrum to longer wavelength, as already explained under section 4.92. For example, when the N-oxochrome NH2 group is attached to a benzene ring, it shifts the absorption band from 255 nanometer to 280 nanometer. B. By conjugation of two or more chromophoric group. Bathochromic shift is also produced if two or more chromophones are present in conjugation in a molecule. For example, as already stated, ethylene shows pi to pi star transition at 117 nanometer. while 1,3-butadiene where two double bonds are in conjugation show lambda max at 270 nanometer. C. By using solvent of lower polarity, it is also possible that to achieve bathochromic shift by using solvent of lower polarity, for example, use of the solvent of lower polarity such as use of a solvent of lower polarity such as hexane produces a red shift in the N to pi star absorption of carbonyl compound. Acetone show lambda max at 264 nanometer in H2O, but it shifts to 279 nanometer when hexane is used as solvent. This is discussed in detail in section 4.10. Second, hypsochromic shift or blue shift. It involves the shift of absorption maximum towards shorter wavelength. It may be brought about as follows. First, by removal of conjugation in a system. For example, protonation of aniline causes a blue shift from 280 nanometer to 203 nanometer. This is because anilinium ion thus formed has no lone pair of electron on nitrogen which can conjugate it to benzene ring. B. By using solvent of higher polarity. Use of solvent of higher polarity can be also bring about hypsochromic shift. For example, the use of a solvent of higher polarity such as water in place of hexene cause a blue shift in N to pi star absorption of acetone, discussed in detail in 4.10. Third, hyperchromic shift. The effect involves as an increase in the intensity of absorption. It is usually brought about the introduction of an exochrome. For example, introduction of methyl group in position 2 of pyridine increases epsilon max from 2750 to 3564. Pi to pi star transition lambda max shift from 257 nanometer to 262 nanometer. Fourth, hypsochromic effect. It involves a decrease in the intensity of absorption. It is brought about by a group which destroyed the geometry of the molecule. For example, when a methyl group is introduced in position 2 of biphenyl, hypochromic effect takes place due to distortion caused by the methyl group. As a result, epsilon max decreases from 19,000 to 10,250. Lambda max shift from 250 nanometer to 237 nanometer. It may be noted that bathochromic shift is generally accompanied by the hyperchromic effect, while hypsochromic shift is accompanied by hypochromic effect. The various kind of absorption and intensity shift has been summed up in figure 4.75. Various kind of absorption intensity and intensity shifts. Solvent effect and choice of solvents. First, solvent effect. The solvent used for dissolution of compound under examination has a profound effect on the UV spectrum of the compound as given below. First, effect on fine structure. As a result of interaction of solvent with solvent molecule and fine structure of the absorption band is blurred out and smooth curve is obtained. This smoothing out of the spectrum requires us for much useful information about complex molecules. The smoothing out effect is more in polar solvent than in non-polar solvent. The fine structure of UV spectrum is the best observed in vapor phase. As shown in the figure 4.8, smoothing out effect of UV spectrum in polar solvent, fine structure of the spectrum in various states, smoothing out of the structure in water. Second, effect on the position and intensity of the absorption maximum. The changing the polarity of the solvent may also lead to the change in the position of the intensity of absorption maximum. Effect on the non-polar compound. In general, change in the polarity of the solvent do not cause any significant shift in the spectra of non-polar compound such as dienes and conjugated hydrocarbons. For example, the absorption maximum of the for non-polar compound is practically the same in alcohol polar solvent as well as in hexene non-polar solvent. Effect on polar compound. Effect on non-polar compounds. In case of polar compounds such as alpha-beta unsaturated carbonyl compounds, the absorption maximum generally gets shifted, which with the change in the polarity of solvent, it has been observed that in that such shift there are two types. First, shift in N to pi star transition, increase in the polarity of solvent, shift in N to pi star transition to shorter wavelength. Example, Willis shift. For example, absorption maximum of acetone is at 279 nanometer in hexane, a non-polar solvent, at 270 nanometer in ethanol, polar solvent, and at 264 nanometer in water, more polar solvent. This shift toward the shorter wavelength is mainly due to the greater stabilization of ground state that an excited state through dipole-dipole interactions, formation of hydrogen bond, or solvation with the polar solvent. As a result, the difference in energy between the ground state and the excited state increases, and the absorption shift towards shorter wavelength. Let us, for example, consider the blue shift of N to pi star carbonyl absorption. The carbonyl group is more polar in ground state than in excited state. Therefore, the extent of hydrogen bonding between the group state and the hydrogen bonding between the ground state and the polar solvent like water and alcohol is much more than between the excited state and the solvent. In the other words, ground state is stabilized to the greater extent and undergo greater lowering of energy than an excited state. Consequently, the energy difference between the two states energy increases, and the absorption shift between toward the shorter wavelength. Second, shift in pi to pi star transition, increase in the polarity of the solvent, shift pi to pi star transition to longer wavelength. For example, red shift. For example, it has been observed that as compared to the solution in hexane, solution of ethanol generally show a red shift of about 100 to 20 nanometer. The shift of pi to pi star absorption toward longer wavelength is largely due to the greater stabilization of excited state relative to the ground state that through the dipole-dipole interaction or solvation. As a result, the energy difference between the ground state and the excited state decreases, and the absorption between two large towards longer wavelength. For example, the molecule of ethylene is more polar in the excited state than in the ground state due to the greater polarity of pi star orbital compared to n orbital. As a result, 2 pi star molecular orbital will be relatively more stabilized by dipole-dipole interaction with the polar solvent as compared to the stabilization of the ground state. Therefore, lesser energy will be required for such a transition, and the absorption toward the shift towards larger wavelength. Third, shift in N to pi sigma star transition. N to sigma star transition are very sensitive to hydrogen bonding. For example, alcohol and amine form hydrogen bonding with the solvent molecule due to the presence of non-bonding electrons on the heteroatom. As a result, more energy is required for N to sigma star transition in polar solvent, and shift towards lower wavelength take place. To sum up, first, if a group is more polar in ground state than it in the excited state, increasing the polarity of the solvent effect shift the absorption to the shorter wavelength. Second, if a group is more polar in the excited state than in the ground state, increasing the polarity of the solvent shift the absorption to longer wavelength. So, for 4.10.2, choice of solvent. A suitable solvent for ultraviolet spectroscopy should meet the following requirement. First, it should be transparent in the wavelength region under examination, should be not be absorbed radiation in the region being examined. Second, it should not be less polar so that it has minimum interaction with the solute molecule and has no effect on the fine structure of absorption band and the position of the absorption band. The most commonly employed solvent is 95% ethanol. It is cheap, it has good dissolving power, and does not absorb radiation above 210 nanometer. In other words, it is transparent above 210 nanometer. Commercially, ethanol should not be used as it contains some benzene which undergo absorption in the UV radiation range of about 280. Some other solvents which are transparent above 210 nanometer are N-hexane, cyclohexane, methanol, water, and ether. Hexane and other hydrocarbons are sometimes preferred to polar solvent because they have minimum interaction with the solvent molecule. Benzene, chloroform, and carbon tetrachloride cannot be used because they absorb in the range of about 240 to 280 nanometer. 4.1 Some characteristic absorption band. Table 4.2 lists the wavelength of maximum absorption and corresponding molar absorptivity or excitation coefficient for some typical ultraviolet band containing the different groups. Thus, table is some typical ultraviolet absorption band or is present at different groups are these benzodiazepine. Woodward's Fisher rule for calculating absorption maxima. By studying the ultraviolet absorption spectra of a large number of compounds, Woodward's 1941 deduced a certain rule for correlating lambda max with molecular structure. Since they are rule have been modified by Scotto and Fisher as a result of more experimental data. It modified name as Woodward-Fisher's rule. Enables us to calculate the position of lambda max from a given structure by relating the position of lambda max with the position of degree of substitution of chromosomes. They calculated value of generally with 2 or 3 nanometer of experimental value. We will now consider these rules briefly for different classes of compounds. First, Woodward's Fisher rule for calculating lambda max in conjugated dienes, trienes, and polyenes. Before we consider the rule for diene, triene, etc., it will be useful to explain some terms involving in the discussing the rule. Homoannular dienes. It is a cyclic diene which contain conjugation about double bond in same ring. For example, given this. Second, heteroannular dienes. It is a cyclic diene in which double bond in conjugation are present in different rings. For example, the examples are there. Third, endocyclic double bond. It is the double bond present in a ring as shown in given below. Endocyclic double bond A. B. Exocyclic double bond. C. Endocyclic double bond and exocyclic double bond both. For ring A has one endocyclic and one exo double bond. Ring B has one endocyclic bond and but only one endocyclic bond. Fourth, exocyclic double bond. It is the double bond between which one of the doubly bond atom is a part of a ring system as shown in figure B. Woodward-Fisher's rule for conjugation diene, triene, and polyene, etc. According to these rules, each type of dienes or triene system has a certain fixed value at which absorption take place. These constitute the basic value or parent value. The contribution made by various alkene substituents or ring residues, double bond extending conjugation and polar groups such as Cl, Br and Or are added to the basic value to get lambda max for a particular compound. The parent value and contribution of different substituent group are as shown in table 4.13. Parent value and increment for different substituent group. Parent value: acyclic conjugated dienes 217 nanometer. Homoannular conjugated dienes 253 nanometer. Heteroannular conjugated dienes 240 nanometer. Increments: each alkyl substituent or ring residue 5 nanometer. Exocyclic double bond 5 nanometer. Each double bond extending conjugation 30 nanometer. Oxochromes OR 6 nanometer. SR 30 nanometer. ClAbr 5 nanometer. NR2 60 nanometer. OCOCH3 0 nanometer. To illustrate the above rule, a few examples are ahead. Problem 4.6. Calculate the lambda max for the following A. In first, the parent conjugated diene plus 2 alkyl substituent plus 2 ring residue plus exocyclic double bond is equal to 217 plus 10 plus 10 plus 5 is equal to 242 nanometer. Second, parent heteroannular dienes plus 2 ring residue plus exocyclic double bond is equal to 214 plus 10 plus 5 is equal to 229 nanometer. 4.7. The parent annual compute lambda max for the following compound: parent homoannular diene plus 4 ring residue plus 2 exo double bond 1 double bond extending conjugation 313 nanometer. Woodward-Fisher rule for alpha-beta unsaturated carbonyl compounds. Woodward-Fisher rule for calculating lambda max for alpha-beta unsaturated carbonyl compound modified by Scotto may be summed up as the given table 4.4. Parent value and increments for different substituent and groups. Parent value alpha-beta unsaturated acyclic or 6-member ring ketone 215 nanometer. Alpha-beta unsaturated 5-member ring ketone 202 nanometer. Alpha-beta unsaturated aldehyde 207 nanometer. Increments: each alkyl substituent or ring residue at alpha position 10 nanometer, at beta position 12 nanometer, at gamma and higher position 18 nanometer. Second, each exocyclic double bond 5 nanometer, double bond exocyclic to 2 ring stimulately 10 nanometer, double bond extending conjugation 30 nanometer, homoannular conjugated dienes 39 nanometer. Sixth, exochrome position OH alpha 35, beta 30 and gamma 50, or alpha 35, beta 30 and gamma OCOCH 36, alpha 6, beta 6, gamma CL 15, alpha 12, beta gamma not defined, BR 25, 30, NR2 95 at beta. In this compound, the actual spectra obtained are affected by considering the nature of the solvent employed. Therefore, the solvent correction is applied to the calculated value of the obtained the values for the particular solvent. However, we are not discussing the solvent uh, correction at this stage. For few examples for the sake of installation are as below the rule. Calculate lambda max for the compound CH3C double bond OC CH3C triple bond CH2. The given compound is an alpha beta unsaturated alicyclic ketone having the alkyl substituent in alpha position. Parent value of alpha beta unsaturated alicyclic ketone is equal to 1215 nanometer 215 nanometer. One alkyl substituent at alpha position is equal to 10 nanometer. Calculated value to 2.7 nanometer. Observed value 220 nanometer. 10th is this. Calculate the compute the value of the structures having the compound in which the calculated value is 259 and observed value is 256 nanometer. Ultraviolet spectra of conjugated enes and enones. It has already been studied that the presence of conjugated system in a molecule play a very important role in the ultraviolet spectroscopy. The molecule play a very important role in ultraviolet spectroscopy. It is a molecular. If a molecule contains two chromophoric groups separated from each other by two or more single bonds, their effect on the UV spectrum to the molecule is generally additive. But if the two chromophoric groups are conjugated, they are particularly equivalent to a new chromophone and are markedly different spectrum is obtained. To illustrate the statement, we have more now considered the ultraviolet spectra of conjugated enes and enones. Ultraviolet spectra of conjugated enes. The UV spectra of all enes, whether conjugated or non-conjugated, involve the UV pi to pi star transition. Still, the spectrum of conjugated enes are markedly different from non-conjugated enes. This is basically due to the fact that in conjugated enes the energy of pi to pi star orbital are much closer together than the simple enes. As a result, the conjugated system require lesser excitation energy as compound non-conjugated system, and therefore the absorption to shift to the longer wavelength. All alicyclic conjugated dienes exhibit redshift of about 40 nanometer with respect to unconjugated dienes, giving intense signal in the region 215 to 230 nanometer. Extended conjugation gives rise to additional red shift along with the increase in intensity. Lambda max value of the following polyenes clearly illustrate the effect of conjugation and its extent on the lambda max of conjugated enes. The values are for ethene, lambda max is equal to 170 nanometer, 1,3 butadiene 2 double bond, lambda max is equal to 270 nanometer, 135 hexa tri-in triple bond gives lambda max 258 nanometer, 1357 octa tetra-in 4 double bond give lambda max 290 nanometer. For B keraton 11 double bond, the lambda max value is 455 nanometer. The UV spectrum of a conjugated diene 1,2,5-dimethyl 2,4-hexadiene of methanol is shown in figure 4.1 for the sake of illustration. UV spectrum for 2,5-dimethyl 2,4-hexadiene is shown in the figure. It may be seen that there is a broad absorption band in the region between 210 nanometer to 260 nanometer, and the absorption is maximum at 243 nanometer. Ultraviolet spectra of conjugated enones. Conjugated enones, example ketone, in which carbonyl group is in conjugation with the carbon-carbon double bond, exhibit strong absorption in the region 215 to 250 nanometer, but due to the pi to pi star transition and weak absorption in the 310 to 330 nanometer range due to the n pi star transition as compared to unconjugated ketones, there is a redshift in both of the types of absorption due to the conjugation. It may be noted that the weak n to pi star band is sometimes not observed at all because it is masked by the very intense epsilon value of approximate 10,000 pi to pi star bond. Lambda max value for pi to pi star absorption band of some enones are given below. For ketone, it lambda max 190 nanometer. For CH2 double bond CH3 double bond OCH3, lambda max is 230 nanometer. For CH2 double bond CH3 C double bond OCH3, lambda max is 218 nanometer. For CH3 twice C double bond CH3 double bond OCH3, lambda max is equal to 237 nanometer. The UV spectrum of the conjugated methyl oxide CH3 twice C double bond O CH3 in ethanol is shown in figure 14.12 for the sake of illustration. The UV spectrum is methoxically. The spectrum shows pi to pi star absorption band in lambda max 233 to the nano n to pi star band lambda max 315 is not observed in the spectrum. Intensity, interpretation of ultraviolet spectrum and application of ultraviolet spectroscopy. The interpretation of ultraviolet spectra of unknown compound can be very useful in deriving the structural information about the compound. The main application of the ultraviolet spectroscopy are as follows. First, detection of conjugation. Ultraviolet spectrum help to show whether